Alrighty, so today we're going to enter a brand new lesson, which is bonding. Specifically, we're going to be learning how to draw chemical bonds. Previously, we've only talked about writing the formulas for different compounds, those being either ionic compounds or covalent compounds. We're going to mainly focus on ionic compounds for today's lesson. So, to start off with, our method of drawing out our different molecules is going to be done via the localized electron bonding model, or LE model for short. And so what the LE model states is that we're going to assume that molecules are composed of several atoms, and those atoms are bonded to each other by sharing pairs of electrons. So essentially, in simple terms, in order to make molecules, you have to connect a bunch of different atoms together, and those atoms are connected to each other by sharing electron pairs. And in addition to this, we are going to assume that electron pairs are known as being localized. Localized electrons essentially are going to stay in one spot and not move from that one singular spot. And so electron pairs that are localized on one singular spot will be referred to as lone pairs. And then there is another pair of electrons, or other type of pair of electrons, known as a bonding pair. A bonding pair is a pair of electrons that essentially connects two atoms together. So if I want to draw an example as to what a molecule looks like that's comprised of several atoms, we can do water. Water is H2O, 2 hydrogens, 1 oxygen, and it looks something like this. It's the 2 hydrogens, each bonded to oxygen, and oxygen is found at the center. And then oxygen has these 4 sets of electrons, or 2 pairs of electrons, that are localized directly on top of them. And so, in order to actually distinguish between them, these pairs of electrons that are found right here, so these two and these two, are referred to as lone pairs because they are localized entirely on that one oxygen atom. Now, there's another set of electrons that are at play in this diagram or structure, and those are this line, these lines that are connecting the hydrogens and the oxygens, because remember, these atoms are bonded together by sharing pairs of electrons. So this line right here and this line right here are referred to as bonding pairs. Regardless as to whether we're working with lone pairs or bonding pairs, at the end of the day, each one of these is comprised of 2 electrons. So the lone pairs that you see right here are both comprised of 2 electrons. The bonding pairs that you see here, each individual one is comprised of 2 electrons. We'll go into more specifics as to how to draw a Lewis structure like that as the lesson moves on, but for now, we're going to keep on talking about the localized electron bonding model. And the 2 components that we're going to refer to are the Lewis dot structures, which will be talked about in this video, and Vesper, which will be referred to as in another video. Lewis dot structures are simply the way that we model valence electrons, so similar to the drawing that I had shown for water. Vesper is simply a way to describe molecular geometry, so the 3D arrangement of these molecules or atoms. Now, before we move on to actually drawing out straight up Lewis dot structures for molecules, I do want to talk about drawing just Lewis dot structures for atoms by themselves. In order to draw a Lewis dot structure for an atom, you need the number of valence electrons. And in order to get the number of valence electrons for an atom, you need to know what group number it's in. So for the A groups at least, you'll just simply look at the group numbers. So for group 1A, you would have 1 valence electron. For group 2A, you'd have 2 valence electrons, etc. And so the only reason why we look at exclusively the valence electrons is because these are the only ones that are involved in actually forming a chemical bond. So even though the inner shell electrons are obviously there and are obviously existing, we're not going to draw them out because, again, we are only paying attention to the bonding in this chapter. So if I wanted to draw an example as to what some Lewis dot structures for just atoms by themselves would look like, here we have magnesium and here we have oxygen. Magnesium is in group 2A, so it has 2 valence electrons. So if I wanted to draw the Lewis dot structure, I'd simply draw it like this. So I put 2 dots right there. You can put those 2 dots wherever you feel like it around magnesium. However, I'm choosing to group them together as a lone pair. And then for oxygen, which is in group 6A, it has 6 valence electrons due to it being in group 6A. So I'm just going to simply draw 6 valence electrons. So I'll draw 2 here, 2 here, and another 2 here. A nice thing to do is to basically just assume that your molecule is in a box and you can only put 2 electrons per side of that box. As a quick note, it really doesn't matter, again, where those valence electrons are placed. It just matters that you get the right amount. So here's a completely different drawing for magnesium, and you can clearly see that instead of grouping up these 2 electrons at the bottom, this diagram has 1 on the left and 1 at the bottom. This is still a perfectly fine structure and is correct. So now we can move on to drawing Lewis dot structures for entire molecules. And so what a Lewis dot structure is a diagram to show how the valence electrons are arranged among the atoms of a molecule. And the most important rule that we are going to follow is that every single atom in a Lewis dot structure must achieve noble gas configuration. If we recall, the noble gases are group 8A or 18. So this essentially just means that every single atom wants to behave like the noble gases, or simply put, have 8 valence electrons. So when you draw Lewis dot structures, every single atom should have a completed octet, or 8 valence electrons. So these are the 3 rules that we're going to follow in order to draw out proper Lewis dot structures. The first is obviously to only show valence electrons, and that these are going to be represented as dots. And then the next 2 rules are for atoms in particular. There is the duet rule and the octet rule. Now, the octet rule is what we just defined right now, so let's get into that. Now, with very few exceptions, every element is going to follow the octet rule, which basically just states that in order to have noble gas configuration, every element needs 8 valence electrons surrounding an atom. So that means that in a Lewis dot structure, every single atom should have 8 valence electrons surrounding it. If every single atom does not have 8 valence electrons surrounding it, well, you have an incorrect structure. One big exception to the rule is for hydrogen and helium specifically. Hydrogen and helium follow the duet rule. The duet rule is what it sounds like. Instead of hydrogen and helium requiring 8 valence electrons, these require 2 valence electrons in order to achieve noble gas configuration. So these are the 2 main exceptions that we're going to be looking at, and more often than not, we'll be looking at hydrogen. Okay, so now that we know the literal definition of a Lewis dot structure, we can go ahead and start writing down the rules and start practicing how to draw these different structures out. So whenever you're given the formula for a compound, it is very important that you follow these rules to a T. So the first thing that you need to do is you need to calculate the sum of the valence electrons from every single atom in that molecule. So you're going to take each individual atom and figure out how many valence electrons it's contributing to the structure, and that is going to be the total sum that you have. Now, we are not going to care at all as to where those electrons are coming from, just the total amount of valence electrons. The next thing that you're going to need to do is you're going to use electron pairs to form a bond between each atom. And there's a specific pattern to this. You're going to put one atom at the center and then connect every single other atom to that center. So we're going to refer to that center atom as the central atom, and we're going to refer to any atom outside of the center as a terminal atom. Now, this is a very specific rule. The central atom must always be the least electronegative atom given in a compound. So least electronegative just means most to the left and down on the periodic table. So that will give you the least electronegative atom. Now there is one rule to this, and there is one easy exception, that being hydrogen. Hydrogens always, always, always will be terminal atoms. So if you ever see hydrogen in a formula, that means that it is going to be a terminal atom and can literally not be found at the center. And lastly, once you do bond everything together, any remaining electrons are going to be used to satisfy either the duet rule for hydrogen or the octet rule for every other element. So once you form every potential bond, you need to use lone pairs to satisfy the octet rule for any other atoms. So let's go ahead and take a look at some examples. Let's start with a fairly simple one, being methane, CH4. This is 1 carbon, 4 hydrogens. So our structure should have 1 carbon, 4 hydrogens. So to start off with, step 1 says that we need to count the total number of valence electrons. So I have 1 carbon, and each carbon has 4 valence electrons. And then I have 4 hydrogens, and each hydrogen has 1 valence electron. So this is essentially just 4 plus 4, or 8 electrons in total. Instead of referring to them as individual electrons, I will instead refer to them as 4 pairs. All I do to figure out the number of pairs is divide the number of electrons by 4. So now I have to pick my central atom. Obviously, because I'm working with carbon and hydrogen, the central atom must be carbon, because hydrogen can never be at the central atom and must always be terminal. So what this means is I'm going to draw my carbon and I'm going to surround it with all 4 of my hydrogens. So now the next thing to do is to draw bonds between each atom. So I'm going to connect every single one of these hydrogens to the carbon. So I'm going to draw a line to represent the bond between this carbon and this hydrogen. At this point, I've used up 1 pair, or 2 electrons. Now I'm going to bond the other set. So this is the second pair. Then I have my third pair, and lastly, my fourth pair. At this point in time, I have used up all of my pairs of electrons and am officially out. So I cannot put any lone pairs anywhere. So now I just need to check to see if the octet rule is being followed for carbon, and if the duet rule is being followed for hydrogen. To start off with the hydrogens, each one of these hydrogens is bound to 1 pair of electrons. Now remember that these electrons are being shared. So what you can essentially assume is that both of the electrons found in this bond right here are shared equally between the hydrogen and the carbon. So you can say that 2 electrons are on hydrogen and 2 electrons are on carbon at the same time. And so we're saying that we have 2 electrons on this hydrogen, meaning that this one is following the duet rule. We can also say the same about all the other ones because they obviously have the same bonding trend. And then for carbon, all you need to do is count the number of pairs surrounding it. Carbon has 1, 2, 3, 4 pairs literally attached to it. 4 pairs refers to 8 electrons, so carbon is satisfied. So now we can move on to a different structure. Let's go ahead and do something very similar, which is NH3. Whenever you want to find the Lewis dot structure, you must first calculate for the valence electrons. So you have 1 nitrogen, each one has 5 electrons, plus your 3 hydrogens with each one having 1 electron. So that gives you 5 plus 3, or 8 electrons, which we can also refer to as 4 bonding pairs or 4 lone pairs. Once again, nitrogen is obviously going to be the central atom, and hydrogens will be on the outside. So we're going to bond each one of the hydrogens to that center nitrogen. When you do this, you should probably recognize that all of the hydrogens are now satisfied by the duet rule, but you have only used up 1, 2, 3 of my 4 pairs, so we do not have the correct amount of electrons drawn. And there's one last thing that we should take note of, and that's that nitrogen is not happy right now. Nitrogen currently has 1, 2, 3 pairs surrounding it, or 6 electrons. In order to add the extra 2 electrons to make it happy, we are simply going to add a lone pair. So now there are 8 electrons surrounding nitrogen. Okay? So make sure you practice drawing Lewis dot structures by yourselves, and have a great day.